So this lecture is on force transformations. Okay, so here is again our transformations. Here's our x's. Here's the x, y, z, t, velocities, momentum and energy, right here. And again, we said how much these look alike right here. These momentum and x look exactly alike. Y and momentum and y, time, energy. They look very, very similar right here. We said there was an invariant right here for that xt, and we said that same invariant right here between energy and momentum. Okay, what I wanted to do in here today is now get another transformation, which is the force transformation. So we want to see how the forces transform, and so we want to see how fx prime depends on fx. Well, what's the definition? We know the definition of force is the derivative of the momentum with respect to time. Okay, now we need to take the derivative of, say, this with respect to time. Well, t prime. Now we've tried it two different ways. One time we just found what dpx was and dt prime, and we divided them. Another time we used the chain rule. I think I'll even use a third way right here. I can just say this is dpx prime dt prime dt. You know, the dt's drop out. I get the same thing, and then we'll just take each of these derivatives and then just divide them. So it's another way of doing it right here. So let's do this right here. We want to say, what is the derivative of this with respect to time? Well, the denominator is a constant, so we'll just leave the denominator there, square root of 1 minus v squared over c squared. And then we just need to take the derivative of the numerator. Well, that's a constant, so we just get dp, the derivative of px with respect to time, derivative of px with respect to time, minus v all over c squared, the derivative of e with respect to time. Okay. And now we'll just take the derivative of t prime, which is right there, with respect to t. The denominator is a constant, so we can put that constant in, square root 1 minus v squared over c squared. And then we just have to take the derivative of the numerator. The derivative of this is 1. The derivative of this is ux. So it's 1 plus ux v over c squared. 1 plus ux v all over c squared. Okay, so the two square root terms drop out. That term will drop out with that term. And then we have dpx dt. Well, that's just fx. So this is equal to fx minus v over c squared de dt divided by 1 plus ux v all over c squared. Now, I don't want to leave that dt in there. What is the derivative of energy with respect to time? Well, derivative of energy with respect to time, that's really a power. Power is dt. I don't want to just call it power. I'd rather say, you remember we said dw or dE, which is the same thing, a little amount of work or energy, is just defined as F dotted with ds. And if I just take the derivative with respect to time here, derivative of E with respect to time, I'll just put this divided by, this is F dot ds dt. That's just the velocity. These are vectors. So this is just F dotted with u. It's the definition of power. It's the force dotted with the velocity. So I'm going to rewrite this as Fx minus v over c squared. Instead of saying power, we'll say F dotted with u all over 1 plus ux v all over c squared. So we've got Fx right here. If we wanted to go back the other way and say, this is Fx prime, if we wanted to go back the other way and say, what is Fx? You just, again, switch the sign of all the v's and change the primes with the unprimes. So this would be Fx prime. Changing the sign of that, so this is plus v over c squared f. Remember, f dot u is really fx ux plus fy uy plus fz uz. Remember when you take the dot product. Right? But I'm just going to call it f dot u. Divide f prime dot u prime. These are all primes over there. And then we change the sign of v. 1 minus ux prime v all over c squared. So there is the back and forth for the f and the x. Now we need to get f and the y. Fy prime, which is dpy prime dt prime, which is dpy prime dt, dt prime dt. Okay, so now we have to take the derivative of py with respect to time. The derivative of py with respect to time, py prime is just py with respect to time. So I can just turn the prime, get rid of it. That's just dpy dt. And the denominator is the same denominator I had before. It's all of this. 1 plus ux v all over c squared divided by the square root of 1 minus v squared over c squared. This is just f in the y. This comes up to the top, square root 1 minus v squared over c squared divided by 1 plus ux v all over c squared. So that's my fy prime. And then we can get the fy. Fy is equal to fy prime times the square root 1 minus v squared over c squared. It still stays minus. And this now changes, so this becomes 1 minus ux prime. 1 minus ux prime, since the v, we change the sign of v, all over c squared. So there is the transformation of y, and z would be just like y right there. Okay, so this is the force transformation, right? We need this because, especially for the next couple of lectures, we're going to be using this force transformation. But let me say something about, first of all, Newton's third law. Newton's third law. What is that? For every action, there's an equal and opposite reaction. And let me also bring up action at a distance. Action at a distance. When do we have action at a distance? Well, let's say gravity right here. You know, if we look at, say, this is the Earth, and this is the moon right here. The Earth and the moon are pulling on themselves over a distance right here. And we said before that the force on this should be the same as the force on that. But when you're looking at Newton's third law, they mean for every action there's an equal and opposite reaction. They mean at the same time. And we know from relativity that the time here is not necessarily the same time over there. So Newton's third law has a tough time with relativity, since if you have action at a distance, if you have two things touching each other right there, well, then that's the same point right there. But if it's action at a distance, these two, Newton's third law can't even hold right there. And if Newton's third law doesn't hold for something like this, then momentum can't hold. So momentum just can't work right here. And you might say, well, wait, what's going on here? It works for all these other problems where you bump in, but that was an action at a distance. I mean, if we look at it, you notice when you took electromagnetism, they never really used momentum in the whole course right there. Right? You didn't use momentum at all. Let's look at let's say two protons. You have a proton here, and you have let's say they're coming at each other, but not a head-on. Let's just say they miss right here. What's going to happen? This thing's going to head off like that, and this one's going to head off like that, right there. So you could think of it as like a collision. But this is action at a distance. This proton is pushing on this one when he's right there, and so on. They never actually touch, so there's always action at a distance. Now, if you looked at momentum at like at this instant, you'll notice that momentum is probably not conserved. That is, the momentum of this coming at each other is not the same as the momentum there. You might say, well, where did some of the momentum go? Well, remember, there's a field in between here. We would say that's an electric field. And there is momentum in that electric field. There is energy in that electric field. So some of that energy and momentum is in this field. Now, when you're a long ways away, momentum is conserved because there isn't any field that's being exchanged between them. There is some momentum being exchanged through this field. Now, if you remember when I talked about when you get down to what they call quantum electrodynamics, everything is at a distance right there. And how do they handle something like this? Well, they have their fields, they're called quantum fields, and so the way they have to handle it is they have to say this guy emits some sort of a quantum of electromagnetic field over to this one right here. Why? Because that way the interaction occurs right here. It's not over here. And then this travels over and then interacts with this. There is no action at a distance. They like to get away from that because they don't know how to handle it with relativity. And so didn't we say that the medium for the electric force, when we went through that whole particle, fundamental particles, we said was the photon. So these exchange photons right here when the two particles come through here. And the closer they get, the more they exchange. Now they call these virtual photons, which means you can't see them right here. So you can't see these virtual photons, but the closer they get, the more they exchange. That means there's energy and momentum transferred over. And we're not going to get into that, but I just wanted to bring that up because there's a big problem when you have action at a distance with relativity, because the time here and the time there are different. So, but if you have this thing emit something, then everything happens right here, and then you just follow the trajectory over, and then everything happens over here. There's no action at a distance. Okay, so the next time what we're going to do is we're going to see how this now applies, not with these particles emitting, but how does just the 4B, what is the truth now on electromagnetism at the 4B level?